this is Janet and Rabia.
Welcome to Everest Physics Academy.
Before we start, we'd like to recommend our Everest Physics books for high school,
where you can find more explanations and solve applications and problems.
In this video, we will apply the general expression of Newton's second law, the principle of conservation of linear momentum, and the principle of conservation of mechanical energy in order to solve our problem, which includes recoil of two blocks, inelastic collision, and elastic collision.
In the shown figure, a light spring of force constant K equal 270 newtons per meter is compressed by 4 cm by means of two blocks A and B. The mass of A is m1 and the mass of B is m2 equal 0.22 kg. A light string is tied around the blocks and the spring in order to keep the system at rest, neglect all friction. The whole system is placed on a horizontal table. The horizontal plane containing the centers of mass of A and B is taken as a reference level for gravitational potential energy. The x-axis extends positively to the left. Part A. Recoil of the two blocks. At T0 equals 0, the system spring AB is at rest and we bear the string. The system is at rest, it means V0A is equal to 0 and the speed of B at T0 equals 0 is also equal to 0. A is ejected to the left with a velocity of algebraic value V1, whereas B is ejected to the right with a velocity of algebraic value V2. Figure 2 shows the trajectories of A and B after ejection. Here is the trajectory of A and here is the trajectory of B. The time interval separating any two successive dots is equal to 40 milliseconds or tau equal 40 milliseconds. Now use figure 2 to calculate V1 and V2. Take into consideration that V1 is the algebraic value of A and V2 is the algebraic value of B. We know that the motion of A after ejection is uniform, so V is given by the displacement over the time. Since A moves along the positive x-axis, so V1 is greater than 0. From the figure, the distance between two successive dots is equal to 2.4 cm, which is equivalent to 24 millimeter, and the time interval between these two dots is tau. Now, V1 equal 24 millimeter over 40 millisecond, we get V1 equal 0.6 meters per second. Similarly, V2 is the algebraic value of the velocity of B equal to its displacement over the time. From the figure, we notice that the distance between two successive dots is 40.8 centimeter, which is equivalent to 48 millimeter. But why we place this minus sign? Since B moves in a direction opposite to that of the positive x-axis, so the displacement of B is negative. So V2 equal minus 48 millimeter over the time tau, which is the time interval between two successive dots. Finally, V2 equal minus 1.2 meters.
Now, part 2. Apply the principle of conservation of mechanical energy to prove that m1 is equal to 0.4 kilograms. Our system is the two blocks A and B, the spring, and the earth. Now let's apply the principle of conservation of mechanical energy between the initial instant and the instant of ejecting the two blocks. Now this is going to be GPE0 plus KE0 plus EPE0 is equal to GPE plus KE plus EPE. GPE0 and GPE are both 0 because the centers of mass of the two blocks are at the reference level. KE0 is equal to 0 because the system starts from rest. EPE0 is equal to 1/2 kx0 squared. KE final is equal to 1/2 m1 v1 squared, the kinetic energy of block A, and 1/2 m2 v2 squared, the kinetic energy of block B. And EPE is 0 because when the blocks are ejected, the spring returns to its natural length. Now, replace each physical quantity by its value. So, the force constant is 270 Newton per meter. The compression of the spring initially is 4 centimeters. So, we divide it by 100, it becomes 0.04 meters. M1 is unknown. V1, as we have seen in part 1, it is equal to 0.6 meters per second. M2 is equal to 0.2 kilograms and V2 is equal to 1.2 meters per second, as we have seen in part 1. So this is going to be M1 is equal to 0.4 kilograms.
Part 3. Determine the linear momenta P1 and P2 of A and B respectively after ejection. Deduce the linear momentum of the system AB after ejection. P1 is given by the formula M1 V1, where M1 is the mass of A and V1 is its velocity after ejection. Now, substitute for M1 equals 0.4 kilogram and V1 is calculated in part 1, which is equal to 0.6 I. Finally, the linear momentum of A after ejection is equal to 0.24 I in kilogram meters per second. Similarly, for block B, P2 is given by M2 times V2. M2 is equal to 0.2 kilogram and V2 is calculated in part 1, which is equal to minus 1.2 I. Therefore, P2 is equal to minus 0.24 I in kilogram meters per second. Now, the linear momentum of the system is the vector sum of the linear momentum of A and that of B. So P after, or P system after ejection, is given by 0.24 I, which is the linear momentum of A, plus minus 0.14 I, which is the linear momentum of B. Therefore, P after, or the linear momentum of the system after collision, is equal to 0.
Now, part 4. Represent these momenta on the figure using the following drawing scale. 1 centimeter on the figure corresponds to 0.06 kilograms meters per second. Applying the cross multiplication method gives length of P1 is equal to the length of P2 is equal to 0.24, which is the magnitude of each linear momentum, over the scale 0.06. The answer is 4 centimeters. So we will draw P1 and P2 with a length of 4 centimeters. Look at the figure. P1 is directed in the direction of V1, whereas P2 is directed in the direction of V2. Let's move to part 5a. Write the expression of the linear momentum of the system AB before ejection. And then we must write a conclusion. Before ejection, our system was at rest. So P before is equal to 0. But as we have seen in part 3, P after is equal to 0. So P before is equal to P after. So the linear momentum of the system AB is conserved. Now, part 5b. Deduce the linear momentum of the center of mass of this system at any instant. You know that the linear momentum of a system of constant mass is equal to the linear momentum of its center of mass. But as we have seen in part 5a, the linear momentum of our system is 0. So Pg is equal to 0. Let's move to part 5c. Is the center of mass in motion or at rest? And to justify. You know that Pg is equal to m1 plus m2 into Pg, but Pg is equal to 0. Now, m1 plus m2 is different from 0, so Vg must be 0, and therefore the center of mass is at rest.
Focus, please. This is important.
Part B, elastic collision. After ejection, A moving to the left with a speed v1 equals 0.6 meters per second makes an elastic head-on collision with a third block C of mass m3 equals 0.1 kilogram initial at rest. Initial at rest means the speed of C before the collision is equal to 0. Determine the magnitude and the direction of the velocity of each block right after the collision. Assume that v1 prime is the velocity of A right after the collision and v3 prime is the velocity of C right after the collision. We know that during collision, the linear momentum of the system, block A, block C, is conserved. So we can write P1 plus P3. P1 is the linear momentum of A before collision. P3 is the linear momentum of C before collision, is equal to P1 prime, which is the linear momentum of A after collision, plus P3 prime, which is the linear momentum of C after collision. So M1 V1 is equal to P1 plus 0, which is the linear momentum of C before collision, since it is initially at rest, is equal to M1 V1, which is the linear momentum of A after collision, plus M3 V3 prime, which is the linear momentum of C after the collision. Since we have a head-on collision, so all the velocities are in the same straight line. So the vector relation can be written in the algebraic form. V1, V1 prime, and V3 prime are algebraic. Rearrange by taking M1 as a common factor on the left side and M2 as a common factor on the right side. Now we can substitute for M1 equals 0.4 kilogram, V1 equals 0.6 kilogram, and M3 equals 0.6 kilogram. So we get equation 1 with two unknowns. As you know, to solve two unknowns, you need two equations. Then, the collision is elastic, so the kinetic energy of the system is conserved. So half m1 v1 squared, which is the kinetic energy of block A before collision, plus 0, which is the kinetic energy of C before the collision, is equal to 1 half m1 v1 prime squared, which is the kinetic energy of block A right after the collision, plus 1 half m3 v3 prime squared, which is the kinetic energy of block C right after the collision. Now rearrange by taking m1 as a common factor on the left side, we get a new equation. As you know, v1 squared minus v1 prime squared is equal to v1 minus v1 prime into v1 plus v1 prime. Now we have got a new equation, which is equation 2. Dividing equation 2 by equation 1. So the left side of equation 2 over the left side of equation 1 is equal to the right side of equation 2 over the right side of equation 1. We can cancel m1 by m1. Also, v1 minus v1 prime cancels v1 minus v1 prime, and m3 cancels m3. We get a new relation among v1, v1 prime, and v3 prime. So we can substitute for v1 equals 0.6 plus v1 prime and move v3 prime from the right side to the left side of the equation. We get a new equation, which is equation 3 plus. We know that equation 1 is given by 0.6 into 0.4 into 0.6 minus v1 prime equals 0.13 prime. Expand, so 0.4 times 0.6 equals 0.24. 0.4 times minus 0.1, times minus v1 prime equal minus 0.4 v1 prime, and take 0.1 v3 prime to the left side of this equation, so it becomes minus 0.1 V3 prime equal to 0. So we have a system with two equations, equation 1 start and equation 3 start. Solving this equation or this system by using your scientific calculator, you get V3 prime equals 0.96 meters per second and V1 prime equals 0.36 meters per second.
Now, part 2. The collision lasts for 0.012 seconds. Use sigma f external equal delta P over delta T to determine the average magnitude and the direction of the force FAC exerted by A on C during the collision. Now take into account that you can take the two blocks A and C as your system, because in this case the force FAC would be an internal force acting within the system. So if you want FAC to be an external force, you must take the system as the block C only. Now, what are the external forces acting on the block? We have its weight, m3g, the normal force exerted by the ground, and FAC. Sigma F external is equal to delta P over delta T. The left side of the equation is m3g plus m3 plus FAC. The right side is delta P over delta T. What is delta P? It is the variation in the linear momentum of block C. Remember that block C was initially at rest before the collision. Now, look at the figure. M3G and N3 are vertical forces, so they do not participate in the horizontal motion of the two blocks. So, M3G plus N3 is equal to 0. This is going to be FAC is equal to M3 V3 prime over delta T. M is the mass of the block C and V3 prime is its velocity right after the collision. Now, V3 and FAC have the same direction. So now we can calculate the magnitude of FAC. FAC is equal to M3 V3 prime over delta T. The mass of C is 0.1 kilogram and V3 prime is already calculated in part 1. It is 0.96 meters per second. The duration of the collision is 0.012 seconds and the answer is FAC is equal to 80 newtons.
Part C. Inelastic collision. After ejection, the block B of mass m2 equals 0.2 kilogram, moving to the right with a speed of 1.2 meters per second, collides with a 40 block D of mass m4 equals 0.6 kilogram initially at rest. D is initially at rest. It means that its speed, denoted by V4, is equal to 0. After collision, the two blocks B and D move together as one body with a speed V. The question now, determine the value of the speed V. But take into account that B moves to the right before collision, so it moves in a direction opposite to that of the x-axis. That means the algebraic value of the velocity V2 of a block B before the collision is equal to minus 1.2 meters per second. Now, during collision, the linear momentum of the system BD is conserved. So we can write P2 plus P4 equal P2 prime plus P4 prime, where P2 and P2 prime are the linear momenta of a block B just before and right after collision, while P4 and P4 prime are the linear momenta of a block D just before and right after the collision. Now, M2 V2 is equal to P2, 0 is equal to P4 since D is initially at rest, and P2 prime plus P4 prime is equal to M2 plus M4 times V. M2 plus M4 is the total mass of the system, and this system after collision have the same velocity V. Now, let's move to the substitution. M2 is equal to 0.2, V2 is equal minus 1.2 I, M2 plus M4 equals 0.2 plus 0.6. Finally, we get the velocity of the system after collision, which is equal to minus 0.3 I. But we have to find the speed. Easily, we can deduce that the speed of the system after collision is equal to 0.3 meters per second.
Now, part 2. Is this collision elastic? Justify. Let's start with calculating the kinetic energy of B and D before the collision. So we have the kinetic energy of block B, which is 1/2 m2b2 squared, and the kinetic energy of block D, which is 0 because D was initially at rest before the collision. So m2 is equal to 0.2 kilograms, and its speed before the collision is 1.2 meters per second, and the answer is 0.144 joules. Let's move to the kinetic energy after the collision. You know that after the collision, the two blocks move as one body, so their kinetic energy is 1/2 into m2 plus m4 in times v squared. So m2 is 0.2 kilograms, m4 is 0.6 kilograms, and their speed after the collision is 0.3 meter per second, as we have seen in part 1. So the answer is 0.036 joules. Now observe the answers. Kinetic energy before is 0.144 joules and after 0.036 joules, which shows you that kinetic energy before is less than kinetic energy after, and therefore the collision is inelastic.
Thank you for watching. If you like this video,
Subscribe to the channel, hit the like button and share.